what I want to talk about is what I think are the obstacles to getting to this model-based system architecting, model-based system engineering involved of that. My mantra when I teach this, I spent 20 years in the industry, worked at Lockheed Martin, worked on the Aegis project to help transition it from a closed system to an open architecture. But tonight, you know, when I teach it now, I say I model or I architect using models to reason about the problem, to understand the complexities, and Jeff, to your point, to communicate with others. If I don't communicate with others as an architect, I fail, okay? And that's a lot of what we have to do. And so I always, when I build my models, when I'm doing this modeling, I always have to keep that in mind. We were talking on the break that there are some, you know, guys and gals that, you know, if they can't put 100 blocks on a diagram, they just go nuts. And in my mind, well, then you failed the course, because if you've got 100 blocks on that, you can't communicate that to anyone else. You know, you need about 3 levels of abstraction in there. I think one of the challenges we have is we really don't know what model-based system engineering, model-based system architecting is. And I propose these are my 4 pillars of MBSE. I know INCOSE's got theirs. But first of all, you've got to deal, when you're a company and you're trying to deal with this, and we did it, when we were at Lockheed, we tried to pick the next system engineering modeling tool, what the next, and we had the software engineers and the system engineers trying to pick a tool that they could both agree with. It became real clear it's not just picking the tool. First of all, you have to worry about what modeling language are you going to pick, okay? And there's a lot of them out there. There's still IDEF, there's SysML, there's UML. So, you know, are you going to be using functional block diagrams? Are you going to be using design-specific languages? You have to deal with the life cycle model. Are we going to follow a V model? Are we going to be more agile? Or, you know, are we going to use a spiral? Are we going to use the incremental commitment model? What model of life cycle? Now we worry about also what's the modeling tool. Are we going to use Core from Vitech or Magic Draw or EA or, you know, any of the host of SysML tools that are out there? Are we going to use, where's that, Doug Dory's OPM? There's a lot of different really good modeling tools out there that you also have to think about and decide, and you have to worry about what your methodology is, because a lot of these languages don't come with a methodology, okay? Am I going to use functional decomposition? Am I going to use Hatley-Purby? Am I going to use Harmony Depth? Am I going to use Iconics? There's a lot of different methodologies. And any one of these decisions with these 4 pillars are going to drive some of the other decisions. And there's no right or wrong order. It's part of what you have to do. I'm not saying a lot about this, but I've done 2 surveys now, one with the OMG about 4 years ago, one with the MBSE about 2 years ago, and it's real clear to me that it's not the tools or the language issue that is the obstacle, it's the cultural issues, the communications issues. So let me take you through the journey. I watched this happen at Boeing, when Boeing decided we're going to start using numerical control machines down in the factory, and he told the aerospace engineers, we're going to this new tool called CATIA. And the aerospace engineer said, you can have my drafting board when you pull it from my cold, dead fingers. And so what Boeing did is they created this new position. They hired new mechanical engineers graduating from school that were not afraid of computers and said, you are now a CAD operator. Aerospace engineers, when you're done doing your drawings, rip them off your drafting boards, hand them to these young aerospace engineers. They will put it into the machine so that we can drive our numerical control machine. That was 1983. Today, you cannot find a drafting board or a mechanical engineer or an aerospace engineer using one. You can find a drafting board in the Boeing Museum, but that's about it. The graybeards today have grown up using these model-driven tools to do this. And sometimes they've got all kinds of multiple heads, okay? I contend you can draw the same story for the software engineering. How many of you heard real programmers use command line, okay? Now no one uses command line. Now they're using graphical user interfaces. I contend that that's where we are in system engineering right now. We are at that cusp of beginning to make that transition. As I put it, it takes a generation or two to make that. These people have got to retire, go away, go play golf, whatever, so that this new way of doing it is going to make it better. So here are the view of my obstacles that we have to face as system engineering, as software engineers. Okay? First of all, we have risk aversion within our, and I said it's a cultural issue, it's a management issue. Our management, they keep saying we want to reward risk, but they don't want to take risk. Sorry to the executives, I don't mean to offend people here. I'm just calling it as I have seen it. Okay? And there's this learning curve, and they see that learning curve as a risk. We had a big learning curve on Aegis Open Architecture when we did this. There's cost. Now, cost, to me, this is a red herring because no one will think twice about spending $40,000 for a CATIA workstation or a hardware workstation for the mechanical engineers, but when you ask them to spend $10,000 for a core workstation or a Rhapsody workstation, whatever, oh no, I can't spend that much money. Okay? But there is a cost issue and there's a training issue. There's the whole knowledge. We're still learning how to do this. The companies that have been doing it, the Rockwell Collins, the Lockheeds, the Boeing, they have more knowledge. They've gathered a lot of this knowledge. Some of it gets shared, a lot of it doesn't. It's still sitting in there. And finally, there's the tools issue. By the way, back here in the knowledge, there's a learning curve for the academics too, because most of us graybeards in academia did not use these tools when we were learning, and therefore we're hesitant to teach them in our own classrooms. And it's hard. That's changing. We got people that are coming out of industry into academia that are teaching them. And I mean, we started when we started the system engineering program here at Stevens. We started using core from the beginning. We've had model-based system engineering in our program. So that's what I see as our obstacles, our challenges, because as we do that, the software folks and the system engineers, we start talking the same language. Right now, we do our diagrams, we throw them over the wall, the software folks throw them away, start with the requirements, and start over. So we've got to think about it.
Thank you, Rob.
Do you think one of the reasons the software guys throw away the models you throw over the wall is because you've compromised design and don't give them enough design freedom?
My experience when that was happening at Lockheed is that they were using IDEF, the system engineers, so they were doing functional decomposition, and the software engineers were writing in object-oriented software. And so they said, we don't know what a function is anymore. Where are your objects? And so they had to go back to the requirements and re-architect their software using objects. So that was my experience of what's happening then.
I agree that the first pillar that you put on the slide, that the language is very important. So don't you think we need to have a set of metrics to make a judicious decision as to what language to choose as a basis for our modeling?
You know, Doug, I would love that. I would love for us to get to one language. We're human, and we're engineers, and system engineers in particular, software engineers to a lesser degree, love to argue. And, you know, we still can't come up with an agreement of what system engineering definition is. So I'd be happy if we could get to 2 or 3 languages at this point. You know, I used to think, oh, it'd be great to get to one. I've given up on that. But I do agree with you. It would be great if we could, so that we could all communicate and use the same words and definitions and what have you. I'm not going to see it in my lifetime.
So when we defined this technical area, we talked about a couple things. One was the relationship between software and system engineering relative to the methods, the process, and the tools. And I think there's another area that we have to, another sort of, if you would, a leg to that chair, and that is talking about the sharing and easy access of information, of this technical detail information. When I first started my, for the first part of my career, I worked for small and medium-sized companies, and I had an opportunity to work in a number of different areas, including systems and software. In fact, we didn't call it systems at that point, but even mechanical and electrical engineering. And, you know, we were able to share information a lot easier. Of course, these were much smaller projects. These were much smaller development efforts. when we get to these large and complex systems, which I think is really where this starts to come in, the companies start to sort of compartmentalize their areas because there are various specialties that are involved. And, so we just naturally, it's just a natural way sort of forming that separation. Well, once we have those different compartments, now we start coming up with ways to share information. As we heard this morning, we learn from our mistakes. We start putting down these details. And the ultimate end of all that is, I believe, is that we start, limiting, cutting off that faucet of information that we're sharing across these different departments. So when I came to Lockheed about 14 years ago, one of the things I noticed right away was the fact that we had all these compartments and specialties and so forth. So I guess from a natural sort of development, when we create things, when you take it down to its simplest part, basically what we do is we're going to do a little, we're going to test a little, we're going to sort of observe those results, and then we're going to adjust what we have to do. In a large complex system, there's multiple of these threads going on simultaneously, and when I get to that observe part, which I think is probably one of the most important aspects of it, I really want to be able to share information, not just the information within my particular domain, but information relative to other aspects of these large complex systems that are also changing simultaneously. And I think because we have this formality in some of these information, these departmental boundaries, if you would, these silos, it sort of causes us not to share this information correctly. So I guess what I'd like to see going forward in the industry, I guess, is the ability to be able to start addressing this issue of being able to view this information and quickly bring up information and views of different perspectives of information so we can make these decisions in these relatively small sort of cycles. So a lot of our focus has been on the process and tools, and that's good. But I think we really do need more information, more focus on this capturing and providing the tools and infrastructure to be able to capture this information, just as we do with Google and the internet. You can go on Google, you can sort of type in something, and bingo, you get a lot of information. I think that's a very limiting factor, is what I see in these large complex systems and large complex systems development.
So Google doesn't have to capture the information that it serves back up to you. How will this happen, in your view, in complex systems projects? Data entry operators?
Yeah, well, I think, we have to develop the tools to help us do that. I think that is the underlying score. I think some of those tools, we just can't, it's not just a SharePoint or some place to sort of drop a lot of information. That information is constantly changing, constantly being updated, and we need to be able to have the tools to help us sort of look at the right information at the right time, the right abstraction levels, et cetera.
So Jeff, I want to thank you for opening the day on communication, because for me, that's where it all resides, even here in the technical aspect. The underpinning of communication actually isn't language. It's stories, shared context, etc. For you to understand this, I need to give you a little bit of shared context about myself. I consider myself a software engineer, a systems engineer, and a manager. I've done all three in my career. So if you see something here, it's not intended to be pejorative. It's intended to poke a little fun at ourselves, at myself, and then go forward from there. Certainly, we understand what the old days were. This was the age of electromechanical systems. That's not a baby programming. That's a babe in the woods. Software engineering was new at that age. And certainly at that time, well, we could drive everything with spec. Okay? Things were relatively stable, et cetera, et cetera. Okay? But the new reality is that babe in the woods now dominates the story. These are the cyber physical systems that we deal with. And so how do we actually bridge this communication gap, particularly as when Jeff talked about it, the environment is changing so quickly, and the technologies that we're trying to solve these problems with are evolving very rapidly. What sits in the middle point for us? We can look to our history, our very recent history, to see a couple things. As these software-intensive systems rose in the 90s, the first thing that we tried to bridge this gap was, hey, they're software-intensive systems. Let's shift the focus to software. That's good. They've got a tool set that works for them. We're going to do away with our system stuff, and we're going to adopt UML. Didn't work very well. Why? UML was not designed for the system space. It was designed for the software space. All right, that's good. We're learning people. We can learn. Let's pass that tool back to them, and let's now try something else. Let's extend UML. Let's make a profile of UML called SysML, and let's basically use that as a communications tool. That's working better than the adoption of UML, but it's not working that well, okay? The emperor has no clothes if we will admit it, and that's what I look at out in industry, okay? Why is that? We got three fundamental problems. Mike Pinotti called one of these out in his position paper, verbs versus nouns. Systems engineers tend to looking at things from a behavioral perspective, and that's where we start. Software engineers, well, the place we start is object identification. Which one's right? Which one's wrong? They're both right. They're both wrong. It depends on what you're trying to do. Diagrams versus models. We have really sold ourselves down the river in calling SysML a language. It's not. It's either a series of languages or it's a diagramming specification. Does that mean there's no value there? Absolutely not. There's real value there, but there's more to a language than diagrams. There's more to a model than independent diagrams. If not, we would have top ML, front ML, and side ML for CAD, and we don't. And the key is the middle. It's syntax and semantics. We have been tending to work this problem at the syntactical and the notational level as we try to bridge this communication gap between systems and software. Not syntactical alone. You must also have the underpinning, the semantic. And we're not, as an industry, fundamentally dealing with that. If you look at the INCOSE roadmap, we've got a disconnect. We're not trying to deal with theory and ontology and formalism still here. In fact, we're trying to mature our methods here. Now, I've preached this for the past couple of years because I have to, and my theory is, look, we're pragmatic people. We've got to deliver. We've got to actually do something. But until we have a shared concept and a shared underpinning, a shared language is not even possible, okay? So if we draw a lesson from DODAF, what do we need? Ultimately, I don't think we should take the systems tools and force them to software. I don't think we should take the software tools and force them to systems. And when I'm saying tools here, I mean processes and methods as well. I'm using it in the holistic sense. The reality is we need a connected underlying semantic model. Linked data isn't enough, and that's the game we're playing. We have to have a connected semantic underpinning. Ultimately, that's the only way to get to the MBE vision, model-based engineering. This is what our customers care about. They don't care about model-based systems engineering. They don't care about the software techniques. They care about faster time to market, higher quality products, everything that MBE will give us, but only if we connect the life cycle. So,
given some thought to this underlying problem of semantics. So basically our systems have function, behavior, and structure. And I've contemplated what kind of underlying semantics could describe those in a consistent way that you could prove that the structure diagram and the functional decomposition are describing the same thing. And I have no solution to offer. It's just a very, very tough problem.
Go ahead, Deb. You can go ahead and comment.
Okay, this really gets back to my previous question, and I totally agree that semantics is at the heart of it, and this is maybe this workshop is a great opportunity to deal with this at some level of depth, because until we agree on this and see how we integrate structure and function and behavior, we will have hard time making any real progress. So I think this is a basic, and I have some ideas, some suggestions, and I'll be happy to share them if I get a chance.
So in a way, picking up on that last point, what's not really talked about is the properties that we're interested in, like availability, reliability, performance, security, and their interaction. I mean, to me, systems engineering is about trade-offs between different aspects of systems, trying to balance the value associated with all those different properties and attributes. And these things like SysML and UML are pretty useless at specifying those things. I've tried to do safety assessments on SysML models and on MODAP, the British version of DODAP, because DODAP wasn't complicated enough, so we added a few more views. But it doesn't actually help you do anything.
And we decided to follow those views.
Oh,
Call it GoDAP 2.0.
oh, my sympathy. I'm sorry about that. So how do we address drawing into these models these other properties, which actually what are interesting? To me, they're actually what drives architecture. Your architecture is to deliver those non-functional, terrible term, those non-functional properties, not the functionality.
At the risk of expanding the conversation beyond the scope that Art has asked us on systems and software, I think the answer to that is to bring different people into the conversation. The model-based systems engineering workshop and initiative that INCOSE has run since about 2006 is absolutely wonderful. If I have one criticism, the problem is there are too many systems engineers in the room, okay? And the real problem is there aren't enough other people in the room. This is not a systems and software dialogue to get the definitions that you're looking for and the modeling concepts that you're looking for into our holistic systems models. We need to pull the mechanical people. We need to pull the electrical people. We need to pull language design people. But right now it's systems and software engineers playing in our own sandbox, and we're not defining the scope the right way or leveraging other lessons learned in the past. We're not the first ones to make this journey. We don't need to completely plow new ground.
One of the things we tried to do at Lockheed, and I rolled off the project before I saw the result, and John can probably give us more on the result, but we essentially started bringing some of those people into the environment, the system architecting, the re-architecting, if you will, early. So we bought our reliability, our maintainability, our testability folks, our safety folks in as we could afford it. The problem you have there on major projects is the funding profile doesn't support that. Our funding profile kind of looks like the technology S-curve, okay? But if you do this thing right and you bring the people on, it should go just the opposite way. So you are only limited in the number of right side of the V people, if you will, or bottom part of the V people that you can bring on in those early phases because you're not funded sufficiently to do that. But by starting to bring them on also and school them, then those things start becoming part of your attributes and start getting incorporated in the model. The modeling tools are still insufficient, okay, but at least you start thinking about them and getting those notes and what have you added into the model.
So what we've seen relative to these models is there is not really a single tool or a single language you can use across. And so what you need to be able to do now is to have these transformations between these and the linkages between them so that to share the right information so it's defined once and managed in one place. And so I think that's the trick. And I don't think, I do think that our tools now, we have to sort of get this message out to our tool vendors so they can start making these linkages and connection points. Some new standards, OSLC is a standard for making some of these linking. I don't think it's the complete answer, but I think it's a start. And I think they're the types of standards and tools to implement those standards and help us automate that interconnection between these various tools is the way to go. We will not capture every single detail in the system architecture model in SysML. I don't think that ever was really the intent. But what we found is that this linking and connection of these various domain expertise and the more detailed information is something we need to do so we can manage this entire environment and sort of realize that underlying information sharing that I was talking about earlier.
OSLC, like SysML, is a great step forward. However, that's syntactical sharing only. Everybody is currently required to do their own semantic modeling, and that is the hard part. The syntax is the easy part, so we need to go a step further.
Yeah, I totally agree with you, John, about the importance of the non-functional, what we call quality attributes early, and I think that can be a communication vehicle of systems and software engineering because they are concerns that cross the boundaries, and they ought to be up front. And, you know, I agree it's been a hard sell to get people to think about those early, but it's key. The second thing is there are languages that have been developed that try to admit some of the diversity among various clubs of systems engineering and articulate concerns about quality attributes. AADL is one of those. I'm not going to preach the value of AADL. But where I think we ought to go is the development of contract languages that would translate between all of these various models, because I don't think we're going to get people to embrace one model or one language or one paradigm, but we need to use some of the techniques that people are using in other domains, in our own domain, to develop contract languages, to use some artificial intelligence techniques and actually mine some of what we have to be able to make the translations and to affect better communication between the players who are important.
Well said, Linda. And I think from the comments I'm hearing just quietly up front, we're in violent agreement. Trying to get everybody to a universal language is a fool's errand. If not, we'll all speak English, or realistically, we'll all speak Chinese. So it's not fair.
So one of the things, and that this is maybe leveraging off the last question just a little bit. So today we have what I call a document-centric paradigm of the way we do systems engineering. And it's more than just, in my mind, just the fact that we write things down in words and it's imprecise, et cetera. The documents provide well-defined boundaries that involve things like intellectual property boundaries and things like that. So now when you move to a model-centric paradigm and you deal with complex systems that have tiers of decomposition with different companies involved, you start to break the barriers between where the IP boundary resides. And that's an issue that I see nobody really addressing or talking about, but I think it's going to be probably one of the biggest issues to kind of getting over the hurdle of moving all the way towards a model-based engineering approach.
No, I agree. And in fact, I think there's another area there we worry about quite a bit, and we work with classified systems. Be able to filter out the right classification level for the right people. So it's the same type of issue. You know, and so right now in SysML, we're going through some evaluation to understand where some of the shortcomings are. And I think that is one of the shortcomings, in that we have to have some way of being able to identify the type of information, the metadata of that information that we're capturing. And one of those aspects is proprietary information security. Classification.
I'm a big fan of putting everything you can in the model. So I think that there might be ways of handling that. You just add another attribute, you know, IP owner. You add specific attributes for the concerns that you might have. Now, that still makes it tough because those fields can be edited. Maybe there's ways of locking them down, just like you do. Some database fields can be locked and others can be edited. But you're right, and again, it goes back to their cultural issues, not technical issues. You know, these are the issues around running a business rather than doing our jobs as system and software engineers. But they are real, and they do drive a lot of what we have to do.
And one additional aspect on this, and I'll call this out because there is a group working on it. What we're talking about is that there actually is something beyond systems and software engineering. I really hate to say that. And we often operate within, you know, an acquisition process. If you look at the gates in the classic government acquisition process, they are actually completely misaligned for a good model-based approach. Now, are we going to go to our customers and dictate that they're going to change those processes? Not overnight. And in fact, they are well tuned to use documents for good reason in legal senses, et cetera. Go try a model in a court of law. It's not going to happen. So the model-based conceptual design working group within INCOSE is actually looking at how do you deal with the contractual boundary, either between the government and the prime and the subs, as a way of dealing with this information control, security, exchange type question. they know it's going to be a long answer. So.
Talk about the value of the model for the current problem at hand versus being able to use that model on future systems and the potential reuse.
Patterns. I think that's one of the things that as systems engineer, I full disclosure, my dissertation was on applying patterns to system architecting. So I'm a lot biased in that direction. We have to get better at that, and we have to get better at how do we mine our existing systems? How do we capture those ideas and those notions at an abstract level that can then be applied forward? And also then realize that you apply patterns where they fit. And for the unprecedented systems, don't go look for patterns because it's unprecedented. But one of the problems I've run in there is the same IP issue. Any company that is using patterns are hesitant or even just flat out will not share them with the rest of the community because they're seeing A as IP and B as a competitive advantage. Which is really interesting because if you go look at software patterns, you can find tens of thousands of them published on the internet. So this is a fairly recent phenomena that we've started clamping down on everything. But I think for modeling, patterns are a natural for modeling. We just have to be smart enough and spend a little bit of overhead, if you will, which is another nasty word, to creating these pattern repositories even within our own companies.
Is there any thought, maybe there's already work I'm unaware of, that rather than saying there is a system engineering model or a system engineering tool, maybe there are different models and tools for different domains. Maybe healthcare, enterprise IT, automotive would have a different way of approaching system engineering, which would lead to different models and tools.
Yeah, as Rob just said under his breath, they do. The relative maturity of that is very inconsistent across the board. Those of us in military aerospace practice tend to like to think that we're leading the curve. In many cases, we're not. Some of the automotive are in fact leading the curve in a number of areas. But you will have to get to domain-specific languages underpinned by a more universal general theory, in my opinion.
At the same time, I have these conversations with Mark Blackburn all the time, another one of our colleagues there, and he's a huge fan of domain-specific languages. And I'm one of those fans of using things out of the box. In a previous life, I was a product manager for Digital Equipment's all-in-one implementation parts of Boeing. And the good news about all-in-one is you could customize it. The bad news about all-in-one is you could customize it. So every time they delivered a new version, you had to go back and revalidate all of your customized applications. So I understand the need for DSL design-specific languages. I see them, but at the same time, I believe that they will tend to fragment our already fragmented system and software community, whereas instead, let's work to try. We may not get there, but can we work to improve what seems to have some momentum right now and improve it so that we don't have the need or maybe reduce the need for design-specific languages? I don't know what the right answer is, and I'm very schizophrenic. If you asked me this tomorrow, I probably would have a different answer.
David, thanks for your comments. I appreciate them. Just a quick idea before I ask my main question. I think, if you look at some of the most recent studies in software engineering, you'll find that UML isn't working very well in software engineering either.
I was being polite.
Yeah, essentially, the most recent studies show that nobody's using it except for quick sketching. And that's perhaps a slight overstatement, but not very much. So let me shift the dialogue from that kind of diagrammatic model to the notion of properties and the methods by which you achieve properties. And where I'm going with this is to ask you to elaborate on the notion of semantics, but let me sort of give a framework for that first. So let me pick just three sort of properties. You know, I want my system to have absence of deadlock. I want it to have physical stability, and I want it to have evolvability and sustainability over a long period of time. I mean, a system is going to be successful when it has all of the properties that are required for it to succeed and to be fit for purpose. So for absence of deadlock, you have to have models about concurrency and maybe some kind of model checking. For physical stability, you have to have some control theory. For evolvability, we don't even know quite what we need to have. Now, you talk about semantics. So in the context of this notion that you have to articulate a full suite of necessary properties, that you have to have different disciplines and languages for dealing with those different properties, where then does your notion of semantics come in, and can you make it concrete for me with an example?
Whether or not I can make it concrete for you, I'm not sure, but let me address the breadth of what you're talking about. This is why, in my opinion, that systems engineering is the last of the engineering to go model-based, because of the diversity of what you just talked about. We can have very clear models that address the first issue, the concurrency, the deadlock. We can have physical models that address the second. The third gets into the higher level concepts that we're trying to capture in systems engineering. Okay, now let's come back to semantics. If you will go back, let's predate SysML by just a couple years and look at a language called AP233. For those in the audience who remember it, Rob's nodding his head. AP233 was derived from systems engineering practice over X years, and it was a language in which we were defining what a requirement is, what a function is, what a component is, not diagrammatically, but actually what is it and what are the interrelationships between those concepts. And the purpose wasn't to exchange data between Doors and Core and Rhapsody. It was to exchange data between systems engineering and mechanical engineering and electrical engineering, because ultimately we're going to need to answer the ultimate dimension of your question. There are multiple models. I'm a big believer that at the conceptual level, there is an integrated system model. At the specific concerns and at the detail level, there are multiple models that drive off that. So hopefully that at least started the answer. And then Anne, and then we'll run out of time, I think.
The reuse comment made me think of something that in automotive, Jaguar Land Rover's executives believe they can drive efficiency up to 40% in terms of their current business practice if they can truly drive the models across the product life cycle. However, the tools they have don't support their ability to do that. So they're having to really work and push their tool vendors to begin to do that. And there's comparable competitors who are looking at the same thing, Chrysler, Ford, for instance, additionally. I think this context, too, David, that you're pointing out, thinking about how some of these concepts transcend domain application and how we can look at that. I'm beginning to think about sort of an integrative way we can look at the contributions of multiple players and domains across the life cycle aspect, and where our tools and methodology need to go with us to enable that.
In the System Engineering Research Center, we have a research task with NavAir, and it is the goal of that research task to help them discover how they can reduce 30% at least out of their 15-year acquisition life cycle using model-based development, model-based engineering. And one of the subtasks that I worked on was to begin to develop the ontology that transcends the multiple engineering domains that NavAir does in developing a fighter or any kind of aircraft that the Navy would use. It is unbelievable until you sit down, and I am not an ontology weenie. There are people that's all they do, and God bless them. But it's amazing, and you don't realize till you start looking at all the different domains, how the terminology is so overloaded. We have limited words to describe some of this stuff. And so looking for that AP 233 or looking for those semantics or looking for that underlying definitions across engineering domains will be very difficult. And I know that there are companies like Jaguar and others trying to do that. But just the simple notion of a model. Model, you have the definition at its simplest is a facsimile of reality. How many up and down levels can you go?
Well, the great news is I think the panelists did a very good job on a number of questions left unanswered, and I appreciate the energy. But we'll have to carry this on through some of our work. Thank you.